Hello everyone, thank you very much for being here. My name is Jordan Alexis Caraballo-Vega and I work for the Science Data Processing branch in Code 587. I'm currently providing support to the NASA Center for Climate Simulation in the areas of artificial intelligence, high performance computing and security. Today I'm going to be discussing some of the work that I've been doing through my Prep 2 time. We're going to go through some of the introduction and methods, and then we discuss some of the results, and we conclude with some remarks. A little bit about me. I was born and raised in Yabucoa, Puerto Rico, best known as the Sugar Town. I started my research career doing research at school in data science applied to nanomaterials, particularly working with membranes. I started my career at NASA via the NASA Muir scholarship. That's sort of my freshman year. Then did a couple of interns with the NASA Center for Climate Simulation, particularly the high performance computing team. Then went through the Pathways program, did some contractor teleworking, and then I'm here. Graduated from school and living the life. Some of the prep overview. So the main assignment is we want to enhance AI/ML processes by enabling the rapid prototyping of projects. And this includes every single step from the development pipeline. We want to develop software that can streamline these processes, but then also perform it as a high-performance computing environments. And also provide additional support to the CSTO office, particularly the iLab team that Mark Carroll leads. Some of the deliverables from this project, a process and an architecture to speed up the development of AI projects, standardized operations to support new scientists, make sure scientists are covered and they do not need to go through a lot of hurdles to get their job done, and then remove some of those operations bottleneck that we have been facing across the AML development community. And just to give some perspective on the Prep 1 project, we were working on, first of all, that human interaction, knowing how earth science data looks like, and then developing the ML software to get a science problem. Now, on the Prep 2, we integrate all of them, including the operations piece, so including that pieces of software development. And the main questions we want to answer is, how can we consolidate and standardize AML project structure? Like, how can we be repeatable since we're going to be doing a lot of this? And some of the challenges, earth science data holding, they're just growing at an exponential rate. We have petabytes of earth science imagery alone. We're just facing a big data problem. And modern era hardware resources have proven to be capable of processing these vast amounts of data. But we need to combine them with AML techniques in order to prove them efficiently and in order to actually keep up with the data we have. And some of these acceleration hardware that provides additional support are GPUs and TPUs. And the fact that we have all of this infrastructure in place, it brings additional challenges. We then need to work with then process reproducibility and how we can trust the models that we're building. We have now complex software dependencies because we need to deal with many packages to get our job done. Installation time and human resources, many of these installations, they depend on having, let's say, someone with elevated privileges to actually install them. So we need to work with them in order to face some of these challenges, and then we need to share our code. We need to make sure that our colleagues, let's say at NASA or even on the outside universities, have access to the code we already developed so we can streamline our development process. And this is how I describe how these challenges look like in real life. So let's say a scientist A and B come, hey, we would like you to AMR project. Here you go. Take 0.3 FTEs, work with us, let's get the job done. Well, this is kind of a deficient start. Engineer A decides to keep rolling, doesn't matter. Let me just ask some of the questions. Well, the engineer had to ask 40 questions in order to get the answers he was looking for. Now we have what data we're going to use, what methods, and then the computational resources that we're going to do. We can start developing the software, but yeah, this was poor time management. We had to spend many hours asking and answering questions. And then once we started doing development, we asked our sysadmins to install the software for us. After 3 weeks of notifying them, he comes, hey, I installed your dependencies. Well, 1 week later, your software doesn't run. And it is just because the sysadmin had to upgrade the system. Well, we're staff dependent here. Now our workflow is going to be ruined because of someone else. Let's say that for some reason, we have engineer A that was working on a project. Engineer A gets sick. Engineer B needs to take on. Now anything of this project that he was working on was documented, not even the data sources. There's no process reproducibility. We're getting to the point where we're screwed. Last but not least, many of our colleagues want to share the code. They want to run it. They want to go through the same results with it. They just can't reproduce it on other HPC cluster. We are creating lack of trust. And this happens on a daily basis. So kind of my proposed and currently active project design is we're going to have kind of a model survey to start with. I'm going to describe each one of those phases to start your AML project. But the key requirements here is all of the documentation must be available via version control. And the main one that we normally use at NASA is Git. The entire process is meant to be iterative and modular. Like every single step in the process can go back to the previous steps in order to get it right. But then communications channels between all of these stakeholders need to be open. We need to be able to communicate easily so we can save time and improve the project lifetime. Let's just go ahead and discuss some of the modular survey steps. This is just the first formal line of communication between all of these stakeholders. And instead of doing this, hey, would you like to AML a project, it is, hey, engineer A comes and replies to scientist, well, yes, let's have this meeting to discuss some of these things. And we have a set of 10 main questions that are going to guide that initial meeting or proposal. Many of us get questions like, hey, how viable do you think this is? Well, answering this survey is going to provide some of those elements in order to know how viable a project could be to even like start a project or even go ahead and write a proposal. This can be modified along the way. It doesn't need to be kind of a static element, but it's kind of a structure that they can start with. And the survey includes elements from all of these stages, from the planning stage, from how we're going to deal with data, how we're going to deal with modeling, and then how far we want to go into our operations. Concise start, structure ideas. We start with creating freedom. Once we have the model survey filled up, we go to the exploratory data analysis. And in here is kind of the first hands-on element of the project. And it's the opportunity for the engineer or even the scientist that is going to be programming to understand the data and its patterns. I designed a concise catalog of AML algorithms and pre-processing techniques to synthesize many of the state-of-the-art and proven research. And this includes from visualization, this includes to the actual, let's say, exploratory analysis of rasters. It's just a one-stop location for the initial review of documentation. We have thousands of papers that go annually on AIML. So we want kind of this concise start, avoid data exhaustion. Hey, these are some of the techniques or algorithms from AIML that could apply to your project. Efficient time management, synthesize information. We can go ahead and start prototyping really quick by just knowing those pieces that we might need to start working on this. Then we go ahead and deal with the dependencies. And this is the most time-consuming step on the entire development pipeline. And one of the proposed technologies to solve this are containers. And containers are an isolated virtualization technology. And think of them as a VM, but at a smaller scale. That has all of the baked dependencies inside that image. So you can install all of the, let's say, Python packages that you need inside that container, and you can port that and share that across different HPC environments. Predictable, easy to manage way of actually sharing your code and sharing your data across different teams. Let's say one of the examples is you have 5 developers working on some code. Each one of them has a different operating system. They have Windows Vista or something else. Just to give an example. They work on this inside this container, so they are OS agnostic, and then they can continue doing the same development without having to support other operating systems. Now, there are some limitations. Every project needs to take care of these dependencies. So by using containers, we can take care of this on a single project, have a container that has most of the dependencies you might need, and then remove that step from your AML development. The response time from sysadmins, you wouldn't even notice this, because once you have your container, you can control your own destiny. You can control what dependencies you want to install inside your container, what actions you want to take in order to start your container. This is the way of streamlining these dependencies and to make these environments reusable. And what I did here is that I designed a simplified and reusable module via DevSecOps techniques to continuously deploy general purpose and application specific containers. And this is how the interface would look like. This is using GitLab, and the scientist only sees, let's say, the container definition file that they want to use. So this is just a file that they want to build a container from. They create a new file that is called a template. And once they start building the template, all they need to specify is what engine they want to build from, and then the name of the container they want to specify. So by only changing these three variables, the users can actually go ahead and build their own containers. Before this step, users would need to know what commands to run, what specific variables to build the container with, and this starts just the build time automatically. And the underlying architecture, and just because the scientist says that, I built a fully automated swarm of nodes via GitOps. So we have infrastructure as code, repeatable, working on our OpenStack cloud environments. We have 16 containers for general purpose, used as kind of the base containers for some of these data science applications, and particularly optimized for the NCCS Prism GPU cluster. So we include all of the CUDA libraries, MPI, and all other fun libraries that you might need. And the only thing that you need to do at that point, if you want to reuse a container that is already there, is just to pull the container. Just to pull down the container, you have the container that you can use. And we just remove that step from the pipeline. Now, unfortunately, there were some cases where some of our users, they needed to build their own containers. The containers that I built and provided across the container arrays here were just not enough for the dependencies. And furthermore, even though they needed some dependencies, building containers is not easy. You're kind of building your own operating system. So installing those drivers and applications, they were just complex. And there were at least 74 lines of code for simply installing MPI and the GPU drivers for your AML frameworks. So I designed a set of tutorials and CI/CD templates for building these recipe files using what is called the NVIDIA HPC Container Maker as the backbone. So the user only needs to know Python, which most of our NASA community overall understand. So we move away from the 74 lines of system code to actually 10 lines of code that is just Python based. This is just kind of an example of how a Docker file before this project would look like. It is just installing MPI, which is one of the multiprocessing frameworks with Monox. This is how it would look like at this time. We have 9 lines of code that we can use to actually build this container. Once we have our dependencies set, we've provided enough support to all of our elements, we go to the modeling stage. And on the modeling stage is now we can actually start developing the software to solve a problem. And as a common practice and just as an advice, this software must be modular and documented so other colleagues could actually reuse it. And as my extension of my Prep1 project, I continue expanding a common library for deep learning applied to satellite imagery. And this library includes the entire pipeline and the entire workflow of development. So it includes starting from the pre-processing of satellite imagery, so calculating remote sensing indices, to the actual final stages of training the model and performing inference and classification. And some of the science products that I've been working on like this, and this is kind of the last stage of the process. And this includes any visualizations that you might want to generate, any artifacts that you might need to complete for the project goal, any other elements that you might need to actually do a good use of your project. And I work on several AML projects along the way of this Prep 2 project. And during the last year, I have been kind of applying these models and fine-tuning the project design so we can leverage across different areas. And the final science product should include all of the software dependencies to produce some of these reproducibility and trustworthiness. And the following AML projects, they did follow the model design that I'm proposing in order to actually save time and reuse some of the underlying dependencies. And then these containers were run both on the Prism and NCCS HPC clusters, but also on the cloud, on our science managed cloud environment provided by Cisco. And this is where we go to this open science effort. Like we want a portable container that people can actually run on other locations, and then reusable and reproducible software where they can work with the data and get their own results. The first project that I was working on is on the segmentation of clouds in very high resolution data. I designed a set of pipelines for training decision trees, particularly random forest and spatial aware convolutional neural networks. So we leverage what is called a unit-based model with encoder and decoder paths to segment these clouds across more than regional areas. So we particularly worked on Vietnam, but then cover areas such as Senegal, and then we're currently working on getting Ethiopia and Alaska for this more than regional project, particularly using transfer learning. And just kind of a point of this project is that both the random forest goes above, CNN goes above the random forest and so on. The second project that I worked on was developing a master CNN architecture and a pipeline for segmenting some of thaw slumps in the Arctic area. And the initial driver of this work was actually identifying these thaw slumps in the Alaska region. What I developed a pipeline for using a master CNN network, which takes into account both the object localization, but also kind of the segmentation of that object, and then return what is called an instance segmentation object, or even just the location of the object. And we got some nice results. We lack of some of the data that we needed to actually finish the entirety of the project, but we proved that this particular architecture is applicable to other areas of research. Another project that I've been working on is developing deep learning pipelines for the segmentation of land cover features in Senegal. Particularly in collaboration with George Mason University, using the same code that we have been working on. And the main objective of this work was the identification of crop and trees for land use analysis purposes. And as part of this, we performed some benchmarking of the recent GPU cluster and some of the new GPU that they brought in for the 100s. So we improved some of the Prep 1 high performance inference pipelines by adding additional mixed precision that has come in some of the latest developments of NVIDIA for additional multi-GPU support. So some of the accomplishments, we developed flexible and modular software framework to utilize across different AML projects. We practice agile methodology for the software development lifecycle and for the releases of software. Built a DevSecOps infrastructure and a catalog of containers for general use, so our users can actually download them without having to create their own containers. And also a software development of several AML related projects, and then hyperfinite involved for these CNN algorithms. On the science side, we have this data survey, this project structure survey. So we kind of start those conversation with scientists efficiently and save time and make this kind of process repeatable. We have an AML core software algorithms catalog, so folks can know how this would look like and how they could leverage some of these algorithms across their data. Develop methods and processes to classify summary resolution data via deep learning, particularly for the segmentation of clouds, and then the segmentation of dust slumps and land cover line use changes. And then generate high accuracy models for the propagation of clouds and land cover from very high resolution satellite imagery. Some of the lessons learned: the hype and excitement of AML is just leading to everyone developing applications. And we have a lot of people developing applications who are not reusing code, so we have many things around that they just kind of do similar things, but they just do not connect. So we need to make sure that we expand kind of our outreach and interaction of information, so we know what other folks are doing in our community. And then the advances in AML, they bring additional and really complex interdependencies. And this increases some of that time spent before getting to the actual science. Time investment is definitely not equal to development achievements. This has been my modus of living for the last couple of years. And then the time management between meetings at NASA is just key to actually get things done. Short blocks of time are just ineffective for publications. Some of the additional tasks that I've been working at the NCCS, I was involved in some additional AML projects that were currently some starting, some finishing. Provided assistance in the upgrade of our critical log analysis infrastructure at the NCCS. This is used for monitoring data analysis and machine learning. Develop two applications to interact with IDMAX, NAMS auto provisioning. So automating some of these manual steps that we would use for provisioning user access. This is particularly like Node.js applications. Additional container support and applications, providing users some of this knowledge and outreach, and then some additional data science applications for calculating indices and other applications. And then last but not least, I was part of the SOUP source evaluation board that just finished a couple of weeks ago. Future work, we planning on closing out several projects with some publications, working on ray tracing for cloud shadows in this very high resolution data, and then exploring concepts of weather and regional generic tracing across very high resolution imagery. Last but not least, then the large scale continuous integration for the entire ML ops pipelines via containers. These are some of the acknowledgements, acronyms, and references, and any questions that you might have.